Hello, good evening everybody. So we are talking about the exploitation of the silicon in industry. So how we can use particular silicon and the purest form of it as well as the silicon dioxide for industrial purposes that we have started in our discussion. So if we think that we can have some silicates also, so silicates are well known and readily available in different types of mineral material. So one type is the typical layer silicates, and these layer silicates comprising of your clay minerals and the micas are quite often we get from the natural sources, and they are often formed by horizontal cross-linking of metasilicate chains. So as we have seen last time, that if you have the typical silicate unit starting from the monomeric one, that means you have one silicon center and 4 oxygens are attached to that particular center, and that silicate ion, the SiO44 minus, is basically nothing but a tetrahedral unit, and the repeating unit of that tetrahedral unit can give like to a chain. And if the orientation of those tetrahedral units are in a 2D layer, we get a layer structure. So this particular one, that means the cross linking of some kind of these metasilicate chains. Metasilicates are nothing but simply the condensation of 2 adjacent silicate units giving rise to a dimeric unit where you have 2 silicon centers and 1 oxygen less compared to your 2 into 4, that means 8 oxygen centers. Because one of the oxygen center is being lost throughout that particular process when you have the corresponding aggregation or condensation between the 2 silicate centers. And you can have also the planar condensation of smaller units. So basically the smaller units are getting condensed and we get different types of structures starting from your layer to a 2-dimensional structure. But if we move from there, that means if you have a 2-dimensional structure, and how we can grow to a 3-dimensional one, and we will consider these as a 3D structures and we consider as a framework structures. So 3-dimensional framework structures are nothing but most common again is your aluminosilicates. As we have seen that your silicate structure will have only silicon and oxygen, but now if we are able to introduce aluminum centers, we will be getting that corresponding aluminosilicates, and they are structurally very complex one, and that is why this some of these silicon centers are substituted by your aluminum center. So if you have a typical SiO2 structure, we should also know that what should be the structure of the pure silica or the mica or the quartz, because you have the repeating unit of the SiO4 unit, and that SiO4 unit ultimately boils down to a structure of molecular formula of SiO2 whole n. Then if we go for replacement of only a particular half or one half of the SiO4 units by the corresponding aluminum centers, that means AlO3 units, thus requires more cation in the structure to balance the charge, because the tetravalent silicon centers are substituted by trivalent aluminum centers. So that means we are getting less positive or the cationic charge to balance the entire charge of the 3-dimensional structure. So once you substitute one silicate or the silicon structure in the tetravalent state by one aluminum and Al3 plus state, we must have one of the cationic part, that means the potassium or the sodium in it, to balance the overall structure, because the whole structure would be a neutral one. And as we have discussed, we will also in future we will also see that the usefulness of these materials, but the examples of these aluminosilicates are feldspars, zeolites and ultramarines. Ultramarines, we all know that ultramarines are very beautifully blue in color, where trapped sulfide ion S2 minus ions are there. Due to that we get a very blue structure, or sorry, very blue coloration of that particular naturally occurring mineral, which is your ultramarine. So we get the feldspar structure, we get the zeolite structure, and we get the ultramarine structure, but the challenge is that how we utilize that, what are those applications, and how we usefully get those materials from the natural sources with slight or little bit more modification of the naturally occurring materials. So some of these silicon based compounds what we can have has a tremendous applications in industry, and the compounds are basically as structural compounds, because we will utilize those as the silicate materials or the corresponding structural part where you have the strong Si oxygen bonds are there, either as a silicate mineral like your mica, like your feldspar, like your zeolite. This can also be a typical SiO2 based structures. That means your quartz type structure or the simple mica type structure or the simplest possible SiO2 structure what we can have. So, from those silicate grade of material, how we can get a corresponding electronic grade silicon, because nowadays we know silicon has a tremendous application in terms of its photovoltaic application, the solar cell applications, because these are very beautifully designed or very beautifully electrochemically considered as the typical semiconductor type of silicon material. So, how we get this electronic grade silicon, that we will see, and the requirements are particularly stringent for p type and n type semiconductors. That means the whole material, the bulk material is of silicon, and we can have some dopants to get a p type or n type semiconductor which will be useful for its application electronically. So, the p and n doped, so dopant are p type or n type. So, p type and n type elements are your boron and phosphorus up to a concentration of 0.1 to 1 ppb. So, very small amount of either boron for one type and phosphorus for the other type we can introduce, because silicon is the group 4b element. So, either you go to the third group or you go to the fifth group for the corresponding doping, for giving you the corresponding p type and the n type elements for your introduction to the silicon structure. So, very ultra pure silicon in industry, we produce it by simply pyrolysis of the molecular compounds. So, in one way how we get this silicon is a difficult one, to get this silicon from the silica or the mica or the quartz material, that means from SiO2, because thermodynamically that particular species, that means that particular molecule or the compound SiO2 is very stable. It is very difficult to break that SiO bond to get the elemental silicon, even if you have the strongest possible reducing agent you use. So, the other way of getting it, that simply you go for very small compound, molecular compound, which are not very much stable like that of your having silicon oxygen bond, but pyrolytically they can break and you go for the corresponding reduction, and sometimes the inbuilt hydrogen atoms there, and those hydrogen atoms can go for the reduction. The way we get it from, say, how we get carbon from methane, or how we get carbon from the natural gas sources or any other hydrocarbons. So, getting carbon from hydrocarbon material is similar to that of your getting silicon from the corresponding compounds which are nothing but your SiHCl3 or SiH4 molecule. Then we can have, apart from this electronic grade silicon, we can get the metallurgical grade silicon, which is treated or reacted in fluidized bed reactor with hydrochloric acid to give SiHCl3. So, metallurgical grade silicon which are not very much pure, but we can treat it in a bed reactor, fluidized bed reactor with hydrochloride or hydrogen chloride. That means it can be your hydrogen chloride gas or the hydrogen chloride in the form of its hydrochloric acid as liquid to give SiHCl3. So, silicon is converted to the corresponding SiHCl3 by a reaction at a higher temperature of 300 degrees centigrade. So, at 300 degrees centigrade the reaction is giving you simply the direct reaction of Si, that means the silicon, with 3 molecules of hydrochloric acid or the hydrogen chloride. That means it is not reacting with 4, it is reacting with 3, giving a particular stabilization of the SiHCl3, not the other species like SiH4 or SiH2Cl2, giving back your hydrogen as the gas material. Then we can have the polycrystalline silicon, that polycrystalline silicon, only silicon, so is known as also polysilicon, is deposited from pyrolytic decomposition of this SiHCl3. So, you get this compound, either you treat it from some other source or the Metallurgical grade silicon, you treat it for SiHCl3 and that can be decomposed at 1000 degrees centigrade to thin pure silicon rods, and we call them as the slim rods. So, SiO2 can be converted to silicon and that silicon to be converted to SiHCl3, and from there we get the silicon in its purest form. So, that is why it is basically a purification process where we get the electronic grade silicon for different semiconductor applications. Now, we move to from there, that means you get silicon dioxide, different materials for its material applications, then different types of organosilicon compounds which have tremendous applications, particularly from the rubber industry, the polymer industry and all this, and this is basically a corresponding silicon analog, that means the inorganic analog of the polymer chemistry. So, organosilicon compounds, basically the name defines you that you can have a typical carbon center which will be attached to your silicon center, that means carbon silicon bond will be there. And this SiC bond is close in strength to the carbon-carbon bond. So, we know that you can have a carbon-carbon chain or a polymeric unit like that of your polyethylene, which can be considered as a simple polymer of carbon-carbon backbone. Now, if we can go in a similar fashion, substituting one of the carbon center by silicon, we get silicon-carbon bonds, and if that particular part, that means the silicon-carbon part, is being repeated, we get the corresponding silicon variety or the silicon analog of the polymer, where you can have the different reactivity pattern, because the carbon-carbon bond strength and the reactivity pattern will be slightly different, though it is, we are saying that is a closed in strength to the carbon-carbon bond, and which we produce industrially can have low molecular silane, we can have oligomer and the polymeric silane. So, these are the materials organosilicon compounds what we can use, and industrially important there are some silanes which are your organohalosilanes. So, which are more important because we can modify those in terms of its organic chemistry attaching to your silicon center. So, organosilicon, what you have the carbon center attaching to the silicon center, then we are bringing halogen. So, organohalosilanes. So, silanes are nothing but your like typically alkanes, we have SiH4 or SiH4 derivatives. So, you bring one organic part, that means you can bring methyl part giving you RSI thing. So, RSI thing, when RSI part is there, it is the organosilicon product. Apart from that, you can put more halogen as X, that can be your organohalosilanes. Then silicon functionalized other organosilanes we can have, because you have the silicon and we consider that silicon center as the corresponding functional group in it. Then other organofunctional silanes we can have. So, these three categories are basically industrially very important, and we must focus our attention for the preparation of these compounds in industry. The first one, thus we can see that it is the organohalosilanes. So, you have the organo part, that means the alkyl part, you have the halogen part, and you have the silicon end. Industrially produced from silicon powder. So, just now we have seen that how we can produce silicon rod, silicon wafer, which we commonly use for your solar cell applications. Then we have the silicon blocks. Then if we can have as a waste material from this silicon industry your silicon powder, sometimes due to the processing of all these things we will end up sometimes with the silicon powder, and this silicon powder along with some alkyl and aryl halides like your methyl chloride or phenyl chloride or chlorobenzene. So, chlorobenzene is a liquid one, is a liquid stuff, and that can be reacted with your silicon center such that the corresponding insertion reaction can take place between your carbon halogen bond or carbon X bond. In presence of some copper and silver catalyst, the reaction can go very smoothly to produce this particular thing. So, what we see that we have the silicon powder, you have the RX material is the alkyl halide or the aryl halide, and the catalysts, some well known catalysts are used such that we react it for R2SiX2 formation. It is not that we are getting RSiX3, we can have also R3SiX. So, all these things are there. So, the control of the reaction, that means the control of the reaction conditions at a particular temperature, catalyst and the different R and X groups. That will tell us whether the predominating product is your R2SiX2 or anything else. So, one such is that particular one is known as Rochow and Mueller process, and this Rochow and Mueller process can be utilized for a derivative where two alkyl functions are attached to the silicon sector along with two halide functions, that means along with your X groups. So, what we do basically this particular reaction, again a well known one. Earlier we have seen, we came to know also that the particular reactor is known as a bed reactor and is also a fluidized. So, the fluid for passing is also available. So, passage of fluid is there, so it is known as the fluidized bed reactor, and that can be utilized for the production of this type of organohalosilanes. Then the variety what we can get is your methyl variety, then R is your methyl or CH3 function, then we get X is equal to Cl. So, we get the methyl chlorosilanes, which are almost exclusively utilized as the starting material for the production of silicones. That means silicon oils, silicon rubber or some silicon sheets of different strength and different solidifying type. So, we get it as that chlorosilanes with longer alkyl groups are produced hydrosylation of alkenes. So, another one category of this is that how you get the chlorosilanes or alkyl chlorosilanes is that simple chlorosilanes we get the hydrosylation reaction of the typical alkene. So, at one end we get this as the typical alkene function, that means you have double bonded CH2 group which is nothing but your alkene material. So, that alkene material when reacted with that of your organohalosilane, one of them is CH3HSiCl2, that means instead of 2 as your R2 group, one is the methyl function and another is the H, because your reactivity pattern or the reactivity potential of that particular silane is different compared to the other one when two of the centers or the two of the bonds are due to your silicon methyl bonds. So, when we use this we get a particular one through the introduction of this particular part, that means the alkene part. So, alkene part through that of your polymerization type of thing is being introduced along with this R function attaching to your silicon. So, any alkyl function, any CH2Cl function, any ether function with some epoxide one. So, epoxide variety is also because the epoxy resins we can make. So, introduction of all these useful functional groups are there on the silicon backbone will be utilized for further modification of the material for their use. So, silicon functional organosilane, what is that? So, you have already the organosilane, but we further consider it as that it is known as the Si functional one. So, the general formula of this is RnSiX4n 4 minus n. That means depending upon the number of alkyl groups. So, you can have one alkyl group, we can have two alkyl group, or you can have three alkyl groups attached to the silicon center, and Al is mostly the smallest alkyl function, that means the methyl function, and X can vary from X to N dimethyl function, that means NCH3 whole 2. So, different types of organic functions based on nitrogen, based on carbon and based on these halogens. So, it is not that we are not able to replace all the halogen groups, that means all the X groups around the silicon, but we will be able to make it a purely organic compound. At one end you have the carbon based functional groups and the other end you have nitrogen based functional groups, in between you have only the silicon. So, these are very useful silicon reagents, and organosilicon compounds are very rich in terms of its organometallic application, in terms of their organic synthesis also, because large number of organosilicon compounds are introduced for pharmaceutical industry, for any other organic fine chemicals preparation and everywhere, because silicon is a useful one for the functionalization of very useful organic molecules. Then we can have organoalkoxysilanes. So, just simply you look at the name where we find that organosilanes are there, organosilicon compounds we have, then the silanes are nothing but you can have further SiH bonds. That means SiH4 is a silane, we know then the derivative of that, that means Si different number of H you can have. So then we can have another organo part, so that means organosilanes are not there even along with that of your alkoxy part. That means OR function is there. So is utilized in different applications, different sectors are getting benefited with the use of this, because of under reaction conditions no acidic cleavage products are formed, as is the case of the organohalosilanes. So it will slightly little bit different compared to your preparation of organohalosilanes, that organoalkoxysilanes are produced from the reaction by reacting organohalosilanes, because your starting material is your organohalosilanes with alcohols now. Because we have seen that it is the alkoxysilanes, so alcohols with the removal of hydrogen chloride. So if we directly react with alcohol, because alcohol is nothing but your ROH, so we bring that RO function on silicon through that. Along with that, you replace the corresponding SiCl bond. So SiCl bond will be lost, and you introduce a new SiOR bond. So that SiOR bond make the molecule to a alkoxysilane form from your organosilane unit. So ordinarily the general formula still you have that R is attached to the silicon center along with the halogens, your different types of organohalosilanes basically. So one organohalosilane, so basically you will see, you try to see that particular part, that means the organohalosilanes, how that can be converted to organoalkoxysilanes. So you directly react with alcohol functions such that the entire amount of halides which are attached to your silicon center, that means you are trying to break all the SiCl bonds, and that SiCl bonds due to that cleavage will be removed as the typical hydrogen chloride, because these hydrogens are coming from your alcohol units. So when R is the different one, R you can have hydrogen to your ethyl function. So all these things are there, because in the starting material what you can have, the typically R you can get as the corresponding H, that means you can have the reaction, same reaction with that where you have the R, that means the R function is attached to the silicon molecule, that means the silicon starting material, and R prime is the different types of alcohol. So two things we are handling, one is R based on the organohalosilicon part, and other R prime is your alcohol part. So giving a mixed type of compound where R and R prime both are present around silicon. How we use this in different useful applications? So application wise they are very useful, because we have now the alkoxy part, because it can be a cross-linking component in silicon rubbers. So industry will be looking for making huge amount of these silicon rubbers, and in the manufacture of different types of silicon resins. So the cross-linking part can be achieved by doing this thing, that means if you can go for this cross-linking from the silicon-silicon bonds, we can get with some bridging units definitely, and also you can have direct silicon-silicon bonds. What we get, that the typical material is basically the silicon material or the silicon oil or the silicon rubbery material, that we can have very useful application. It can also be an adhesion promoters. So the adhesives and the adhesion nature can be improved with the use of these molecules as the promoters with special organofunctional groups. That means when we use to get it as a glass fiber layers. So we have the glass, that means some types of glass fibers we get it. So this glass fiber can be layered within the glass sheets. So this can be considered as a different types of glass fiber layers, or in the formulation of corrosion resistant paints, because these are oil type or a rubbery material. So if we can have use this in the making of the paints or in mold construction, because this particular one will be more robust one compared to its organic analog, that means the corresponding carbon variety. Then what we can see, that we can have now acyl oxysilanes. So what are those acyl oxysilanes that we can now see? So these acyl oxysilanes are, therefore we can have the acyl function, the oxy group, and the silane function. So that corresponding one, the corresponding ether functions, the way we have introduced that ether function from the alcohol unit by reacting with the organohalosilanes, this acyl oxy one can be achieved through the introduction of, not through direct introduction of the OR function attaching to the silicon center, but CO extra is the CO which is your acyl function. because we all know that what is the difference between the alkyl function and the acyl function. Alkyl function is the corresponding methyl function, say where you have the direct methyl group which will be attached to the silicon center, making that silicon center is a corresponding organosilicon variety. But if we are able to go for a corresponding CH3CO unit, so that CH3COO or COO unit, that means the acetate function, so RCOO unit can be attached to that particular silicon which will be acyl oxy function. So, acyl group like your acetic acid, what is your acyl function? Acyl function is your CH3CO function, and if we can have the corresponding acetate function, that means CH3COO which we get for the corresponding esters, not that of your corresponding ethers, because ethers can have ROR function, but esters are RCOOR function. You can have a carboxy group in between the two R functions. It can be different, one is R, another is R prime. So, this is then you bring acyl function, then along with that you have one oxygen center extra. So, that is why it is known as acyl oxysilane. So, general formula would be Rn Si OCO R prime whole 4 minus n, because your limit is there, the 4 is the limit. Either you can have the compromise for the number of R groups or the number of acyl oxy groups. So, R and R, the corresponding availability of these groups are there. R you can have as H, R you can have as the corresponding alkyl function, or R you can have the corresponding aryl function. So, these H, alkyl and aryl functions, when they introduce to the silicon backbone, along with that R prime function, because the R prime functions are different, which can only be attached to the corresponding acyl end or the acyl oxy end. This can be methyl function, or this can be, very interestingly, this CH double bond CH2 function, that means the allyl function. So, how we can introduce? So, we will be doing something which is very much close to your typical organic chemistry, because in organic chemistry we know that the around carbon center we can have different types of molecules and all these things, but when we have a material type of thing, silicon based materials, it can be a oil, it can be a rubber, it can be a resin. So, we can functionalize those resin, we can functionalize those oils through the introduction of some other functional groups which can be further polymerized. That means the introduction of these groups, say you see here that CH double bond CH2 group, which is nothing but your allyl function. So, this allyl, or suppose if you have a carbon, so 3 carbon center is the allyl, it can be vinyl. So, this vinyl group you can have. So, vinyl, we know that the vinyl polymers and the vinyl rubber and the vinyl things are there. So, if along with that silicon, if you are able to polymerize that vinyl end, so that vinyl end can be polymerized and to get is different types of other material which can be further useful for some other important purposes. So, we can have, you have the corresponding number, that means the corresponding acyl oxy numbers are 3 in number, that means you can have 4 minus n, n is value is equal to 1. So, R, that means the alkyl function which can be your H even, or alkyl or the aryl function attached to the silicon is in number of 1, and 3 acyl oxy groups are attached to it. That means whenever you have the 3 groups attached to it and you can modify further, you can get the cross-link product, and which will be a 3-dimensional different types of network built upon your silicon as well as the acyl oxy function. So, is utilized as cross-linking agents in silicon sealants. You see, we are talking about oil, we are talking about rubber, and we are talking about resin. Now, some sealing agent, that some part industrially important parts are in the building or in some other areas where you want to seal some crack, or you seal some of the passages where the water or the any other material, oil or alcohol or anything can come out from that container or the corresponding reservoir or the drum. We can use it as a very useful sealant, and sometimes it can so happen that, as we have seen, that you have vinyl function, and in presence of air, basically if you can have the corresponding epoxy function as well as vinoxy, the vinyl epoxy resins we all know. So, that vinyl epoxy resin in presence of oxygen of the air can polymerize further, and that particular sealant, when it is in absence of air within the tube, is in the liquid form or in some emulsion form. When it comes out of the tube and it goes for the reaction along with that air oxygen, it can be solidified, so it can seal that particular part. So, the basic idea of this thing, how reactive material based on silicon you can make, and it can also be produced by reacting alkyl trichlorosilanes with acetic acid or acetic anhydride. So, if you can have alkyl trichlorosilanes, so you already we have seen that alkyl function R is there, such as that methyl trichlorosilane is nothing but Me3SiCl. So, that can be reacted with acetic acid or acetic anhydride, because both of them, both acetic acid and acetic anhydride, can supply the corresponding alkyl oxy function to the silicon center. So, if you have a very trivial starting material, what we have seen already, that introduction of the silicon in alkyl halides, a methyl chloride, you get the corresponding alkyl halide type of thing. That means you can monitor the number of alkyl functions. If the alkyl functions are more, what we have seen, but if the alkyl function, the alkyl group is less, you can have the more number of Cl groups attached to that particular silicon center, and you directly react that with the acetic acid as well as your acetic anhydride. So, the reactions are very simple and very straight-cut one. Only thing that for the production of alkyl oxysilanes, we have to use RSiCl3, which are nothing but methyl trichlorosilane. So, in both the two cases, what we get the corresponding one where you have 4 minus n value is equal to 3, that means n value equal to 1, that means R will be only 1. So, one alkyl group will be attached to the silicon center, and silicon will have 4 bonds, which is a tetrahedral center. One will have the corresponding carbon center, that means you have one silicon carbon bond, and others are silicon oxygen bonds, which have the corresponding strength, as we have seen earlier, that the silicate material or the silicate minerals, all of them are oxygen. That means the corresponding bond strength of silicon and oxygen is very much important. Similarly, in the terms of its organic backbone, instead of carbon oxygen bond, now you have the silicon oxygen bond, while you make RSiOAC whole 3 molecule, that will be of a different types of molecules. So, in our next class, we will see the application of some other important silicon based compounds, where we will be able to use this, and you will be able to go for these direct reactions starting from your alkyl halosilanes or the corresponding acetic acid or the acetic anhydride. Thank you very much.